In the previous chapter, we saw that we can have uncemented sediments that even though they don't have any force or any cement holding grains together, they can resist a shear stress. And the shear strength, which is the maximum shear stress, is proportional to the effective confinement and the friction coefficient. So what about now materials that are cemented? Well, we are going to have to extend then the the properties or the knowledge that we have right now in order to accommodate that cementation. And in order to do that, we're going to start with what is called the unconfined compression strength. A test of unconfined compression strength is a test in which I load the rock on one direction while keeping the stress on a perpendicular direction equal to zero. These tests are conducted usually on specimens of rock. Let's imagine this is a cylinder that the length is at least twice the diameter of the sample. And that's going to help the experiment to be done correctly, because if it is shorter than that, you're going to have something which are called end effects that are going to affect how the material fails. So ideally, we're going to fail a slender sample, also not too slender because you might have buckling, but in between 2 to 3 times the diameter of the rock. So basically what we do is we load it, in this case in axial direction. We measure what is the maximum stress that the material can hold, and that's going to give me the strength. Okay, now let's put this into the Mohr circle. Into the Mohr circle, as we saw in the previous lecture, what I have to do is I have to plot on the x-axis the principal stresses, which in this case are going to be the radial stress, which is equal to 0, and the axial stress, and in this case is going to be the maximum value at failure, or the peak value that this signature stress and strain shows. And when I plot that Mohr circle, that's going to be representative of the state of stress of this element at failure. The maximum value of axial stress that I can apply is what is called unconfined compression strength. And although it's called unconfined compression strength, ideally, if we did things correctly, this material is going to fail because of shear, not because of purely compression, but because of shear. And let me hold on a little bit on this. We're going to see why that a little more in detail when we talk about the next example. But before I do that, let me share a video of an unconfined compression test done in the laboratory at UT Austin. Let me see if I can go full screen over here. In this case, let's play the video. I'm loading a rock axially. Here I have the load cell that allows me to measure the stress, and I'm going to try to pause it whenever it breaks. All right, probably you saw a little bit of sand or material also coming out from the top. It's starting to break, and very soon, when I get to the maximum value, the sample is going to break. All right, something that I want you to notice is the angle of failure in this case. With UC, it's if we consider it with respect to the horizontal plane, it's in a steep angle. And let me come back and play it again. Let me see if I can move it slowly. All right. So here it starts to fail. And as I told you, ideally, this sample is going to fail in shear at a given angle that we're going to find the meaning for that in just a minute. After the sample fails, of course, you know, the pieces fall apart, and all I'm left with are these two parts of the sample. Okay, so let me come back over here. I'll post the link of this video so you can also play it back and forth. Here is that plane. Here is a plane of failure. And that's, as we're going to see, is related to the friction angle. Okay, this is what is called the unconfined compression strength test, or also UCS. For it, and this is done for a cemented rock. We wouldn't be able to do this in an uncemented material. All right, let's now add a confinement to this material. And now I'm going to have a test of confined strength, which is usually done in what is called an axisymmetric triaxial cell. In this axisymmetric triaxial cell, what I do is I apply an effective stress on the sides of the sample, and I also apply an axial stress which is different than the radial stress. In practice, this is done through what is known as a triaxial cell, like for example this one, and the effective confining stress is applied through a fluid, or I would say with a fluid, through a membrane, impermeable membrane, that transfers that pressure into stress on the rock. And this is very similar to the coffee package that we mentioned in the previous lecture. It's the same mechanism, but now I can apply with this device a much higher confining pressure and confining stress that I could with just atmospheric conditions. Usually, the higher the stress that you want to recreate, the thicker is going to be the pressure vessel that you need. And usually these, for low stress applications, are done, the vessel is done with acrylic, like in this example. Inside you have your sample, and for high pressure applications, and that would transfer for places which are very deep in the subsurface, you will go to something made out, instead of acrylic, made out of stainless steel. And if you want to test bigger samples, then probably you will go to something a lot bigger, like this example over here. So notice the scale. So here you have a baby, just to see what the scale is. And let me show the image of that picture. In this triaxial cell can get up to 1,000 megapascals, which is quite a bit. And this triaxial frame, it's larger than 10 feet tall. Okay, so depending on your application, you might have your triaxial cell, but the principle is the same, is to elevate the confining stress to recreate conditions in situ. All right, so let's come back over here. And now that we see that we can apply an effective radial stress, then I could run another test, not unconfined with sigma r equal to 0, but now with a sigma r which is different than 0. We said before that for sigma r equal to 0, then I'm going to find a maximum value which is going to be the UCS. If I increase now the radial stress, I can run a very similar test to what I ran before. Now, instead of measuring just axial stress as a function of axial strain, I'm going to measure the difference between axial stress and radial stress, and I'm going to increase the axial stress till the sample breaks. And that peak value is going to tell me what is the axial stress at failure. And this axial stress at failure is going to be this value of the axial stress, which depends also on the radial stress. Here I have 2 circles only, but usually in practice you do more than just 2 tests. You'll do 3 or 4, in which you'll have more circles that will help you define this line. So what is this line now? Similar to the case before, this is the line of shear yield or shear failure. And since it is a line, it's going to look like with an equation like y equal to xb plus c, and this is what we have over here, in which I have a component that depends also on friction. This is the frictional strength part, very similar to what I had before, that gives you the slope of the line. But I also have one more component, which is called the cohesive strength. The cohesive strength is the value of the shear stress at an effective normal stress which is equal to 0. Physically, you may think of this as a cementation parameter. The higher the cementation of the rock, the higher this cohesive strength value is going to be. Mathematically, it's just a fitting parameter, but physically represents how much cementation you have in a material. All right. Now that we know that, we can expand this shear strength equation for cemented materials. And again, that's going to be usually done with a triaxial cell. All right, so let's try to explain now the angle of failure. This angle that, as we can see over here, it occurs at a steep angle with respect to the horizontal plane. All right, the explanation is here, and I'm not going to go through the full derivation, but you can work with the geometry of this problem, and you will see that the friction angle is related to the point at which the sample fails in the Mohr circle. And this point gives me the conditions of shear stress and effective normal stress at which the sample fails. And something very important to keep in mind is that failure is going to happen at the plane which has the highest ratio of shear to effective normal stress. And at that plane, that happens to be oriented at an angle in the Mohr circle, which is 45 degrees plus the friction angle divided by 2. And that angle is measured from the plane of the maximum principal stress, which in this case is the axial stress. So the axial stress is applied on a horizontal plane, and the plane of failure is going to be at 45 degrees plus the friction angle divided by 2. If you remember, we said that these friction angles are usually in the order of 30 degrees. So 30 degrees divided by 2 is going to be 15 degrees. 45 degrees plus 15, that's going to give you 60 degrees. And 60 degrees is more or less the angle that you see over here. Let me go to full screen over here. Is the angle from the horizontal plane to the plane of failure, which is going to be the same if I were to measure this on the top, from the horizontal plane to the angle of failure. We're going to see this angle quite a bit in the rest of the class. So remember this angle, 60 degrees. 60 degrees is more or less the angle at which you would expect a shear failure to occur. 60 degrees from the plane where the maximum stress is applied. We'll see that faults, the orientation of faults, are also related to this angle later on. All right, let's go into also exploring a few other parameters. And let me just jump here to the plots. So we have seen the physical explanation of how we have this shear failure equation, which is equal to shear stress is going to be equal to the cohesive strength plus the friction coefficients times effective normal stress. We know that. And we also know that the stronger the rock, the further this component is going to be, the further away is going to be from the origin. And also, if I have a higher friction coefficient, this line is going to be steeper. And if it is steeper and it's higher or further away from the origin, that means that my Mohr circle can grow bigger and bigger, that I can hold higher and higher stresses. All right. Usually what we do in order to measure this yield stress is, instead of working directly with effective normal stresses and shear stresses, we rather work with the principal stresses. So you can run these experiments that we ran before. Let me go quickly through that again, in which we measure what is the maximum axial stress for a given radial stress and summarize all that data in a plot of principal stresses. And this is going to look like this, where the least principal effective stress is going to be sigma r, and sigma 1 is going to be the maximum axial stress. So, for example, for a given value of sigma r, let's say 1 megapascal, I'm going to be able, let me start with the simplest case. If I have no confinement, sigma 3 is going to be equal to 0, and the maximum stress I can apply on that rock on the axial direction is going to be the UCS. If I increase the effective confinement, sigma 3 is going to be different than 0, and let's say if it's 1 MPa, then the maximum stress that can be applied in axial direction is going to be given by this equation. And usually what we do in the laboratory is we test the strength of the rock at several values of effective confining stress. We plot that as a scattered data into this plot, and then we fit a line to that, and from there we get these two parameters: the unconfined compression strength from all our tests, not just from one, and this parameter Q, which is a parameter that depends on the friction coefficient, and it is equal to either this equation as a function of friction coefficient or 1 plus the sine of the friction angle divided 1 minus the sine of the friction angle. Friction angles typically are around 30 degrees, so let's just use 30 degrees in this case. Sine of 30 is going to be 0.5, so 1.5 divided 0.5 is equal to 3. This parameter Q, it's about 3. And for example, for an uncemented material without any cementation, it tells you that the maximum principal stress in a given direction is going to be equal to more or less 3 times the minimum principal stress. And this is quite important because this sets a limit on what is the maximum stress that a sediment or a rock can hold. And in general, for the subsurface, we're going to see this is also quite important because it relates to the effective horizontal stress. And it's going to also limit what is this effective horizontal stress based on the value of the effective vertical stress and whether we are on an active tectonic setting or a passive tectonic setting. We'll come back to this later on. But remember, another important number to remember is 3. 3 is what is called the maximum stress anisotropy for an uncemented material. So, two important numbers to remember then: 60 degrees the angle of failure, and 3, the maximum stress anisotropy or ratio between stresses between for an uncemented material. All right, there is one more thing I'd like to touch related to this topic, and it's that so far we have just talked in terms of effective stresses. All of these equations are valid for effective stresses. What about if we have a pore pressure and I'll come back to this later on. What about if we have a pore pressure which is not zero? Well, in that case, if I have a pore pressure which is not zero and I have total stresses, I need to convert those values of total stresses to effective stresses. And what it's seen in most rocks is that it doesn't really matter about what is the value of the total stress, but the strength of the rock is going to relate it to effective stress. So if I do have a pore pressure, I need to correct my values of total stress to effective stress in order to find this shear failure line. So for example, as I was telling you before, here we have a plot of the maximum axial stress effective as a function of the minimum effective stress, also effective. The higher the effective confined stress or least effective stress, the higher the axial stress, effective axial stress I can apply on the rock is going to be. And that's going to be independent on what is the value of pore pressure. For example, here I see several experiments with different pore pressure, and at the end of the day, when you correct this to effective stress, all of these tests conducted at different pore pressures are just going to fall into one line. All right. One more thing to add to this case is just I'd like to close with this plot over here that shows a summary of typical values of strength of rocks. And you can see that, let's look for example here at the intersection with the y-axis. The intersection with the y-axis is directly the unconfined compression strength. And we see that there are some materials like sedimentary rocks that might have an unconfined compression strength up to 100 megapascals. 100 megapascals is it's quite a bit. It is about that would be about 15,000 psi, and usually carbonates, metamorphic rocks, and igneous rocks are stronger and could have a unconfined compression strength up to 200 MPa. So this is where your granite countertop is. It's quite a strong rock. And remember that strength is also going to depend on the effective stress. The higher the confining, the higher the least effective stress, sigma 3, also the stronger the materials are going to be. And this friction coefficient is also going to depend for each material. In this case, we see, for example, that granite has a large friction coefficient opposed to, for example, mudstones or conglomerates that usually have a lower friction coefficient.